Welcome back to your system design series. This video, we're actually going to talk about some of the most important terminology you should be familiar with as you start studying the rest of these lessons. Now, one of the first things I want to talk about is scaling an app from just a few users to potentially millions of users. And we're probably going to start that process in the next lesson because I want to get some foundational stuff of system design out in this lesson. So this will basically be a very brief intro to a bunch of different topics and keywords you should be familiar with, but you don't need to understand them at a very intimate level. This is really just so when you see these words in the future lessons, you have an idea of what that means and it's not completely brand new to you. So really, this is just designed to give you that 1,000-foot view of everything we're going to be talking about, but you don't have to leave this video knowing every single word in a lot of depth. Now, I just wanted to first show you this beautiful system design that my wife wrote up here. This was for the previous video's thumbnail, but we're not going to leave that up, so I'll just erase that real quick. Oh, snap. Oh, no. Before we get started, I wanted to share two resources with you. The first is a backend software engineering mind map. This is going to share with you every technology you should know if you want to become a backend software engineer. The second thing is if you need help applying the principles that we teach here, as well as the things on the mind map, then I have a mentorship program. This is where you can get one-on-one help to learn the skills to become a software engineer and get a high-paying software engineering role. So if that's something you'd be interested in, I'll have a link for that, as well as the mind map down below. So the first word I want to talk about is distributed systems or distributed computing. The idea of something being distributed is running it across multiple computers. So we'll just say distributed computing. And these are pretty general terms, so we're not referring specifically to the backend or the databases, but pretty much anything could be ran in a distributed environment. We will get into some concepts that apply to specific sections of our application, such as the database level, but now we're just thinking pretty general. Anytime we want to run an application, but it's distributed across multiple computers, we're working with distributed computing. Pretty sure I just used the word in the definition, but the idea is instead of running your service on a single computer, you might run this on multiple computers, and all three of these, in this case, have to work together to give a single result. So we have to start talking about ways to get multiple computers to work together so that we end up with just a single result. So this is going to introduce a lot of challenges, many of which we'll talk about in this series. So a lot of the next words that we're going to talk about build on the idea of distributed computing. The first one I want to talk about is availability. So in the situation of what we just had, where we had three computers working together, this is likely a highly available system. If one of the computers goes out, the other two servers will compensate, taking the load that was originally given to this computer. So if we put a circle around this to basically say, hey, this is one unit, and somebody makes a request to this service, this request could go to any of these nodes. And if we structure it to be highly available, if for some reason this node is down, the request would not go to that node. It would just be redirected to one of the other nodes. So that's the idea of availability. Our goal is to be available 24/7. This is impossible, so we want to get as close as possible to this, and we'll talk about that now. Now, because it is impossible to have a service that runs 24/7 guaranteed, there are different levels of how available a service should be, and these are measured in nines. So 1 9 would be 90% of the time, which means in 1 year, the service could be down 36.5 days, which is 10% of a year. So 36.5 days of potential downtime. Now, it doesn't necessarily mean the service always is down 36 days out of the year. This will be a worst case scenario if a service said that they were guaranteed to be up at least 90% of the time. Then we would have 2 9s, which would be 99%. We're getting a little bit better. And while that might sound nice, like, hey, it's up 99% of the time, still pretty bad because this would be 3.65 days. So that's 2 9s. If you go to 3 9s, it would be 99.9. 4 9s would be 99.99. and you can keep adding 9s to get as close as possible to 100% of the time. Every time you add a 9 to your service, it becomes more difficult, but low numbers like these are super easy to achieve. When you start getting to 5, 6, in a higher number of 9s, it's going to become more challenging. But if you have a service that goes down almost 4 days once a year, that's pretty terrible. At minimum, if you're looking for just a ballpark, shoot for 4 9s. This translates to less than an hour of downtime per year, which for some things, that's not going to work. You know, if you're working on some medical system or some financial system or military system, an hour of downtime could be pretty bad. But in many apps, if an app goes down a couple of minutes here and there, and over the course of a year, it's less than an hour, that's pretty good for many apps. So this would be a benchmark, and if you need it a little bit more serious, then just add additional 9s and start looking for ways to achieve that. We'll get into some of the ways you can increase the number of 9s for your services. So if you don't feel like this is adequate, we're going to talk about ways you can achieve more than that. But this is just a starting point. To summarize that, as the number of 9s go up, so does the availability, which I'm just going to write HA for high availability. However, the costs are going to exponentially increase, as well as the general challenge of implementing the service. So more cost and more challenge, especially something to consider if you're hiring developers. They're going to cost money. So not only will the services you pay for, such as database hosting and servers, go up in cost, but the actual skills required to implement things and keep everything running is going to go up as well. And that ultimately could come back to cost. Next up, we have reliability. And this is a service's ability to do what it is supposed to do. So you can imagine you have a service that's up 99.999% of the time, but the service is non-functional or it's doing something incorrect, such as doing some database stuff where data is being lost. This would be a problem with reliability. And this is a little bit more abstract or hard to measure. And when you're defining what reliability looks like in your app, you can define those rules. So it's not something where it's just, hey, here's a certain number of 9s. It's more abstract. You have to think about what the application should be doing and what success looks like and what failure looks like. But this is a general term to refer to the ability for an app to do what it is supposed to do. So does the app actually work? Even if you have, let's say, 6 9s of uptime, you might have 0% reliability. This setup is kind of like if you have a friend who's always available, you can call them, text them, they'll answer, always get back, and they'll help you with anything, but when you actually need them to come over to help you move, they don't show up, or they show up and they're totally useless. They're always available, but they're not reliable. Two different concepts, so just to kind of get that straightened away in your mind, availability is about the ability to access a service. The reliability is about, is the service functional the way it should be functioning? Next big word you should be familiar with is consistency. So this has to do with everybody seeing the same data at the same time. This is really only going to be a concern when you start working in distributed systems. If you have one computer, one server that's serving your application, you are always 100% consistent. Because the definition of consistency is everyone sees the same data at the same time. So everyone here is probably going to refer to the clients trying to access this server. So if you have a web server, this could be the backend API, and people are trying to retrieve data through some front-end application. So we'll get into more of all of that architecture throughout this series. But for our little example here, we can imagine we have 2 people and they're both on their computers. Dang, that is a really good looking computer. That one, not so much, but we still love you. And because both of these clients are retrieving data from the same source, they're going to see the same exact thing. They are 100% in sync. They are consistent. There's also a term, eventual consistency, which we're going to get to in a second, but let's just go with this for a second. You're either going to be consistent or not consistent. So let's go through the scenario where now instead of having just a single server, you have 2 or 3 or more servers. So now we have a scenario where we have 3 servers. You could imagine these being database servers where these are storing data, and each one of our clients access a different server. The question of consistency is if all of these users are requesting the same piece of information, let's say the user with the ID of 5, are they going to get the same result? There's a scenario where they might not, and that is if instead of just reading the data from one of these clients, we actually updated it. So let's say we changed the user's name from John to Caleb. If our service is not consistent and these clients request that user information, they might get the outdated information. So this change would eventually propagate to this server and this one too, but that takes a little bit of time, right? It takes time to copy that data over. So if we make these requests at the perfect time, right before that data is copied over, we might get inconsistent results. So let's go through the scenario. We updated from John to Caleb. So this server is going to see Caleb because that data is in that server. And then let's say that change propagates to this server. So when this computer tries to retrieve that user information, it will also get Caleb. So far, so good. However, this one, it didn't quite copy that data over in time, and the request retrieves old data that hasn't been updated yet. So this one's going to retrieve John, which is not correct. The results are inconsistent. I know I'm probably drilling this idea into your head a little too much, but just understand when people say consistency, it truly means, are you getting consistent results across the server? In this scenario, you're getting John, Caleb, and Caleb. So with this scenario, if you were asked, is this database setup consistent? The answer would be no, not consistent. However, when I'm saying consistent here, I'm specifically referring to strong consistency. So that's another word you should be familiar with. And strong consistency means when there's a write that happens or some kind of change, that change is going to be available immediately on all of the nodes. There's another type, which is eventual consistency. And that is basically when there is a change, eventually that'll be copied over to the other nodes. It's just not immediate. So let's erase this and then talk a little bit more in detail about the differences between strong consistency and eventual consistency and which one is correct or which one you should use, or what you'll typically see. So if we have a distributed system that is strongly consistent, the way this is going to work is it's going to wait to confirm the change until all of the other nodes can also apply that change. So just to save space here, I'm going to draw those 3 nodes in a line here so we can have some more room to write. And we make some change to the data on this node. That change will be in a pending state. It's not confirmed yet. Until that change is propagated to the other nodes and they have that change locally and they can all be applied so that the change is confirmed. So in this situation, you're not going to see any inconsistency because the change is applied to all of the nodes at the same time. The major downside to this is it's going to take time. We now have to wait for that change to propagate to these other nodes before we can see that change confirmed on the main node we're working with. The major benefit is consistency. The other type of consistency we're going to talk about is eventual consistency, which in my book would be not consistent, but it's still a form of consistency because the other nodes will eventually get the data. It's just not going to be immediate. So with the eventual consistency, we're going to have the same setup. Let's go with 3 nodes here. And we make some change to a node. So we update some data. This will be immediately confirmed. And then eventually that change will propagate to the other nodes. So there's a scenario if you access the data immediately after it's written to the right node, that will get some inconsistent state. And we're accessing stale data. And this would only happen if you manage to access that data before that propagation happens from the main node. Can't really erase that blue too well. So we could say it propagates to this one, but it's not quite done propagating to this other node. So when we access the data, we get stale data. So one client might receive something different than another client. The person accessing this node will get the up-to-date data. The person accessing this node, since the propagation has completed, will get the up-to-date data, but the person accessing this node will get stale data, the old data before it was updated. So the major downside here is that the data is not consistent, which means it's kind of not trustable. The major benefit, and I'm drawing a down arrow so don't be confused, because we are going to reduce the time to write data. We can write data and we don't have to wait for that to be confirmed on the other nodes before we can confirm the entire transaction. So it's not a question of which one's right, it's a question of which trade-off do you prefer. In an environment that's strongly consistent, you're going to have consistent data across all the nodes, but it's going to take a little bit more time to write data to the database. In an eventual consistency environment, you're not going to have that consistency right away, but the time to write is going to be much faster. Which approach you take depends on the application. So I'll write some scenarios where you might choose one over the other. So a big one is going to be banking. You can imagine a scenario where you transfer $100 is the last $100 you have, and now your account says 0, like usual. The problem here is that someone could access your data on another node and still see that you have $100 and then make another transfer. Or that difference might make the difference between getting approved for a loan or not getting approved for a loan. So anything dealing with money should be consistent. Other examples would be potentially medical stuff, especially if it's real time. Stuff that's like electronic health records, probably not a big deal to be strongly consistent because that data doesn't change very often. So it's really about reading old data. Consistency is really important when we're talking about new data being added or data being modified. Another example might be military. You definitely don't want to have inconsistent state when you're trying to decide if you should fire a weapon. Like that's something where you want things to be consistent. There is another big issue here which has to do with availability and the cap theorem, which we're going to get into. But basically one of the downsides of strong consistency is that it can harm your availability. So we're going to get into that. But this scenario would be if you have a medical scenario or a military scenario where differences in data could be detrimental. So I'm going to write these in parentheses saying maybe, just depending on the use case, but definitely probably want to keep strong consistency with anything financial. So let's talk about eventual consistency. Some examples of when you might prefer this route would be social media or other basic CRUD apps, create, read, update, delete. Basically websites or apps where you're changing some data. You might post a status, but if that doesn't show up for people for a couple of seconds, it's really not that big of a deal. You're not doing any real-time trading or anything like that, so it's not the end of the world if you get some stale data, especially if it's only stale for a brief period of time. Next up, we're going to talk about scalability. And honestly, of all the words, if you're talking to somebody in marketing or the CEO, as long as your app is scalable, that's all that matters. So you can ignore all the other stuff. So it's a buzzword, but there's a lot more to it. What does it mean if an app is scalable? The summary is that your app is able to support an increase in the workload, which could come from a spike in traffic or particular parts of the year. Maybe Black Friday, you need more computing power so you can support the new users. One of the easiest ways to achieve scalability is with over-provisioning. So if you imagine this being your server that runs your application, and we're not going to get into splitting out the database and the backend API. Let's just keep it general here. This is our application, and inside of the server, you have a certain amount of computing power, CPU, RAM, and even storage, whether that's hard disks or SSDs. And let's say the utilization of the server is down here. So you're really not using all of your computing power, maybe 20%. So that's okay. And you could probably go a little higher, but as you start to get to using the majority of your computing resources, now you're going to start having issues. And I'm going to say that that's bad. So you want to have a little bit of space between how much computing you need, which in this case, what we wrote was right here. This is what we need, and the max you could support. So from day to day, you don't want to be capped out, but also consider the cases where you might have spikes. Perhaps it's a certain time of day. Every day at 8 a.m., you have more traffic. So you want to consider not only the typical usage, but also what might be the most usage that you need. So this is just a visual to show how much computing power you might need compared to how much you have available. You might only be using half of the available processing power, for example. If the amount of compute you need for peak usage is well within the max, then you have a scalable service. Because even in the worst case scenario where you hit that peak usage, you still have all of this space. And you want to avoid getting into the areas where you're almost maxing out the computer. So let's say there are scenarios where typical usage is well within the realm of this computer, but there are certain times, maybe once a year or once a quarter, where you need even more than what's allowed in this server. You're going to have to do something else to scale this app. So there are a few different approaches to scalability beyond just over provisioning, having some massive server and just hoping you never reach the max. What if you do reach the max? What do you do? There's a couple of different approaches we're going to talk about. The first one being vertical scaling and the second one being horizontal scaling. Vertical scaling, the idea is simple. We just add more computing resources. Practically, that means if this was your previous server, you can upgrade getting a new server or adding more processing power, more RAM, but we still go from one server to one server. It's just a stronger server. This is often also called scaling up. We're just increasing the computing resources, but we're still within a single server. Horizontal scaling, on the other hand, is actually adding servers. So instead of just having this little server, you could have multiple of these little servers working in unison. Or you could do a combination of both. But just to finish this real quick, this would be scaling out. The combination would basically be not only adding servers, but also increasing the computing power. So that might be going from this to now having even bigger servers. So it might look something like that. So a single server may not have been able to scale enough, and even increasing some of the computing power might introduce limitations if you're at a really large scale. So you can go from one server to 2 or more servers. And now you should be able to maintain enough computing power to handle all of the requests. So this might happen, say, once a year. The actual frequency would vary completely based on what kind of app you're building. But the challenge is you probably don't need max scaling all the time because applications often grow and decrease in their usage for various times of the day or various times of the year. So a very similar word, but a little bit different, more focused on the ability to grow and shrink, is elasticity. So with scalability, when there's an increase in the workload, we just increase the compute. So it looks like this. However, this may require manual intervention, and it's typically more worried about the increase in workload, whereas elasticity deals with an increase in workload and then eventually a decrease in workload. When the workload is higher, we will increase the computing power. And then when the load is lower, we will decrease the computing power. So elasticity is the ability for an app to automatically adjust based on usage. Now that might be confusing, like how could you just always be adding hardware and removing hardware? And typically it's going to be done by some cloud provider. So when you're looking at cloud providers to host applications, you can check to see if the service is elastic, and it will do the growth and decrease behind the scenes for you. And because these applications are often virtualized, they might not actually be adding a processor to your computer and then removing a processor. They just have a bunch of servers that will run all of the applications and then allocating more or less resources for any particular application. So that's how a cloud provider can easily allow for elasticity without technicians being in there manually adding and removing hardware all of the time. So these words are very similar and you might hear them used interchangeably, but if we're going to try to be as clear as possible, I would say scalability is focusing on having enough computing power for an increased workload without having your application shut down or, just completely break. This can be achieved various ways, whether that's manual intervention or some automatic setup, even if it's just over provisioning and having more hardware than you really need. One step farther would be elasticity, where the compute is automatically adjusted either up or down based on the current workload. Now, just to review and make sure we're all on the same page, the scalability does not refer to a service's availability. You could have one server that you just increase the amount of computing power it has to increase the scalability, but that doesn't necessarily mean it's highly available, because you could still have one server, and if that server breaks, well, your entire service goes down. Doesn't matter if you have the most powerful computer in the entire world, if it goes down for some reason, you're still kind of screwed because you don't have any backup computers. So that idea is known as a single point of failure. So a single point of failure, you can think of it as any link in a chain that does not have any kind of high availability or redundancy. So that's another word we're going to write down here. So redundancy is just having an extra there in case something goes wrong with the main one, kind of how you would have a spare tire with your car. If you have a flat, you can swap out one of your wheels with the spare and you can still function. It's often the case that in real life, people think of redundancy as a bad thing. If something's redundant, we don't need it, so get rid of it. However, in computing, it's usually the opposite. We want redundancy. So redundancy is usually a good thing. A single point of failure is usually a bad thing. So we're going to make sure this is really clear, drawing these faces. Redundancy, it can add cost, but it can make sure a service stays available. Consider the case where we have some database server, and let's say we're connecting to this from some advanced backend, which has load balancing and a bunch of servers. So this is great. There's no single point of failure here. And then we're connecting to it from some advanced front end as well. So checking if these have redundancy, let's say the front end does have redundancy, the back end has redundancy, but we get to the database layer and it does not have redundancy. This would be our single point of failure, and when we're trying to build highly available systems, our job is to identify single points of failure and try to remove them with various approaches. The usual first step would be to add redundancy. So if we add in a stand-in server, which is just going to act as a replacement if the main server fails for some reason, you can imagine this server explodes, the data center disappears, something terrible happens. Well, this server is ready to go, has all of the data the same as this server. It's consistent with the main database. This would immediately be promoted, and our traffic would route to that new database instance. This stand-in is a little bit different than the backend where we might have multiple servers all sharing the load. The stand-in in this scenario does not take any of the traffic typically. It just acts as an emergency fill-in if something goes wrong with the primary database. So that is an example of redundancy. Anytime we add redundancy, we're probably going to add cost because we now have to maintain two database instances. Another important word you should know is fault tolerant or fault tolerance. So we created a fault tolerant system, a system that will still function if something goes wrong by removing single points of failures. And we removed a single point of failure by using redundancy, having a stand-in database in case something goes wrong. So fault tolerance, that's a general term to describe what we did. We created a system that is tolerant to faults by adding in new things such as redundant servers. So by removing single points of failures, we can achieve fault tolerance. And we do that through adding redundancy. The specific thing we did to introduce redundancy in our application is database replication. So we pretty much just created a replica from the primary node to the secondary node, which that's another word we've been throwing around, but the term node just means one of the computers in a multi-computer setup, where a computer is a server. So a node is a server, which you can just kind of think of as a computer designed to run something such as a database. For some of you who've worked with databases and servers before, that might be super obvious, but if you're just a beginner getting started, people throw a lot of these words out without really describing what exactly they mean. So a node would just be one of these, or this would be another node. And the idea of replication is creating a duplicate node. Let's zoom in a little bit more on databases and talk about some terms with that. So when we're working with the database and we get to the point of not just having a single instance or a node, and we actually want multiple nodes, it might look something like this. You could call this entire thing a database cluster. Now, when you're talking about databases and database clusters, there are various setups you'll see. So this isn't going to be the only way you'll see it, but a very common scenario is you'll just have one master node and then the rest being slave nodes. Or you could just say that this is a write node and these are read nodes. So we kind of showed this already earlier, where you write to a node and then that data is given to the other nodes in the system. So you can think of both of these as replicas. And then it's just a matter of, do we want these to be strongly consistent or eventually consistent? So we already understand the idea of consistency, and we already talked about how if something is consistent, it takes more time to make that right. But to get a little bit more technical on the terminology, when we make these replicas, the act of replication has two different approaches, which would be synchronous, which would be consistent. And what this will do is it will replicate the data over, and it will do it synchronously, waiting for the result. So all of the nodes have to write the data in order for the data to be confirmed. So nothing different than what we've already talked about with consistency. It's just you might also hear the term synchronous replication. Comparing that to asynchronous, which will basically just send data over as it gets it. Not really worried about the time it takes for that data to be confirmed on the replicas. So this node can still be doing things while these other nodes are writing that data. And that's the whole idea of it being asynchronous. So that is eventually consistent. Now the change in time that synchronous replication is going to cause is called latency. So latency is just a measure of how long something takes from request to response. So say this is me, and if we're just talking about general latency here, I make a request to a web page, and that web page shows up after, say, 100 milliseconds. This is the idea of latency. But you could obviously split that out at different levels. So we could talk about latency at the database level, and when things are consistent, the latency is going to go up. So just another word you should be familiar with. It's going to worsen the overall user experience because the time from request to response is longer. Now in this scenario, we just have one primary node and then two read replicas. When we're getting deeper into database clustering, it could be the case that we have multiple write nodes. So what if we not only wrote to this node, but we could also write to this node? That's going to introduce more interesting challenges. And while I think this is important to understand, the first step in terms of growing your app for scalability and availability would be to introduce reading nodes and just directing read traffic to the read nodes and write traffic to the write node. However, if we want a multi-master setup, then we have to talk about more advanced database clustering techniques, which is probably something we're going to get into in more detail later on in this series. So for now, for our basic example, just imagine there being a single write node and then multiple read replicas. That's usually pretty good because it's often the case that applications will be more read heavy and not write heavy. So you might read 80% of the time and write 20% of the time. So you can have more read replicas and individually scale these, keeping just a single write node. And then when it comes to redundancy, you can have a backup write node that's not actively used for writing, but acts as a stand-in if for some reason our write node goes down. We can direct traffic to the stand-in node, but they're not both being used for writing at the same time, which introduces various other challenges. So if you don't have multiple write nodes, the structure is pretty simple, even though I drew a bunch of complex lines and circles here. The general idea is you just have a write node, possibly a stand-in node for redundancy, and then you will have read replicas, which are either consistent or eventually consistent. We have talked about a lot, and a lot of database stuff as well. We're going to do a little bit more about databases, but this time we're not going to talk about databases with replication in a distributed environment. Instead, we're going to talk about just a single database instance, because even on a single computer, there are certain rules we want to enforce to make sure our database is usable and trustworthy. So you may have heard of the term ACID, not like the stuff that like melts stuff or like the drugs, but ACID in databases. So you may have heard of databases being ACID compliant, and what in the world does that mean? That's what we're going to talk about. This is an acronym for 4 different properties of databases. Now, this is what most databases are going to strive for, and most relational databases are going to be ACID compliant. There are certain databases out there that do not meet all of these expectations for various reasons, but this is a general starting point. So if you're working with a typical SQL database, such as Postgres, this is going to be an ACID compliant database. So we're going to go over these very briefly, and we may do a dedicated video to this topic, just depending on how much information I want to cover on these things. But I just think it's a good idea to know that they exist and be lightly familiar with what they are. So atomicity, I believe that's how it's pronounced. Basically the idea of something being a single unit. You can think of an atom even though you can split atoms. A good example of this would be if you run a transaction. The transaction will either succeed or it will fail. It's one unit. You can't have any partial completions. So transactions will either succeed or they will fail. Consistency, this can be a bit confusing because we've been talking about consistency this entire video, but this consistency is actually referring to a different kind of consistency. So why they're not consistent with the usage of the term consistent is beyond me, but the consistency here is referring about state changes in the database. So when you do some processing, your database starts in one state and will move to another valid state. So this is a valid state and this is a valid state, meaning any change is required to adhere to any kind of integrity rules you set at the database level. So we haven't gotten into a ton of the details of databases in this series yet, but an example would be referential integrity. So I'll just write up here, respecting foreign keys. So you can't create a change in the database that breaks some defined rules that you created for the database. This helps your data have integrity, which means it's correct and trustworthy. Isolation, you can think of individual transactions as being isolated, not dependent on other transactions that might be happening concurrently. So I just put independent execution. I was trying to think of a way to describe it without using isolation in the definition. This would be kind of cool one to go into in more detail because that's pretty vague. So you can look into concurrency stuff with whatever database you are using. And then durability is basically data permanence. Once the data is committed or saved, it's permanently saved even if there was a power outage right after. That saving is a checkpoint, and you wouldn't ever expect to have your system go back to before that committed data. So you can trust changes to persist in an ACID compliant database. Another database word I want to talk about is sharding. And this is a specific type of database partitioning. So 2 words we need to talk about real quick. So database partitioning can happen at the individual database level or within a larger database cluster. So within an individual database, let's just say we have one database server, you might have some massive table. This table might be massive because it has a lot of columns. So you can imagine it being split up a lot this way. And one individual row might have a ton of data because it has data for all of those columns. So you could optimize performance with this table by splitting up the table into multiple tables. Typically, you're not going to have to do this unless you're really working with big data, but it would look like this. You split it, and now we might have a table with this section and a table with this section. And then you can just connect rows with a foreign key. So this would be vertical partitioning. Horizontal partitioning works pretty similar, but instead of splitting by column, we'll split the data. So you can imagine if you had a bunch of rows, you can split the data so that the rows are split up instead of the columns. So for example, this row might be assigned 1, this one might be assigned 2, and then this one might be assigned 3, and then again 1, and then 2, and so forth, where now if we wanted to just access a certain subset of this data, such as anyone from partition 1, we would only be working with 2 rows instead of the entire data set. So you can imagine the 1s, 2s, and 3s being split up across different tables, kind of, and then it's just a matter of knowing which table to access to get the correct information. So again, we're just going very surface level. We'll get into partitioning in a lot of detail, so don't feel like you have to understand all of it in this video. The general idea is we can reduce the row count by just working with a subset of the rows. In this case, just my made-up example of labeling them 1, 2, or 3. So that is an example of horizontal partitioning. So this can all be done within the same database instance. So within Postgres, for example, you could just split up your table into 2 different tables with a subset of columns. Or Postgres supports horizontal partitioning, so it can basically do this for you and then give you like a virtual table to see all of the data. Whereas creating the virtual table to see all of the data over here would be to create a view. So again, we're getting into the details, but basically partitioning can be done at just an individual database level without having to worry about replication or distributed computing. However, if you want to take this idea and go one step farther across different nodes, that is what sharding is. You might be able to use those terms interchangeably, but typically when people are talking about sharding, it's because they want to split the data up across nodes. So then instead of just having replicas for fault tolerance and potentially independently scaling the reads and writes, now you could actually split the data across multiple nodes and only have, for example, in this case, a third of the data to deal with. So you can imagine assigning each one of these to its own database node. So that is a very high level of what sharding is and how it works, but there's a lot to it, and we'll get into, how do we decide how to split up this data? How does that work inside of a database cluster? Because it's not always the case that the database cluster will have complete nodes. Sometimes they will just have a subset of the data because they're using sharding. And I'm saying sharding, not sharting, by the way. Wow, we went through a lot of material, introducing many different topics. My goal here was to give you the intro to each major topic, so now you have a better idea of what we're going to conquer in greater detail in the upcoming lessons. So the takeaways from this video, dang, applications can be pretty complex behind the scenes. There's actually a whole other world that I didn't introduce, which is caching. That's something we're going to do dedicated videos on, so we're not going to get into it in much detail here. The main thing you need to know about caching is it's a way that you can temporarily store data for easy, fast access to reduce the computation needed on the API or the database layer. So if we can remove a substantial number of requests that need to be made to the database, we probably don't have to worry about all of this crazy database setup stuff nearly as soon. The main thing you would just want to do is have the availability by having that stand-in node, and then just scale your node vertically, not having to worry about complex clustering setups. Another takeaway from this that you will benefit from, which we didn't get into a lot, but there's various cloud services you can use that will often abstract away a lot of this for you. So for example, you might be using a cloud database, and that cloud database might be serverless. And this doesn't mean that there is no servers being used for the database, it just means that it's fully managed. So you pay for use, and it is elastic, basically growing and shrinking completely hands-free. This can get expensive, but it's very convenient because you don't have to worry about a lot of the stuff we're talking about here. So there are a lot of options out there where you basically pay for usage and it's fully managed, which could actually be beneficial if you're accidentally over-provisioning your servers. You might be wasting money. So having either elastic features with that main server or just going completely serverless could actually save you some money. So just definitely something you should look into and at least be aware that serverless databases are a thing and can be pretty handy. They'll do all of the clustering and database management for you behind the scenes. At this point, you have a pretty good idea of the general structure for software architecture, and now going into the upcoming videos, you'll be much more equipped to fill in knowledge and learn all of these things at a deeper level. I look forward to seeing you in the next video. If you've enjoyed the content, please be sure to subscribe and check out my resource links down below if you want some additional help and useful resources. Thank you. I'll see you in the next one.